come now see, I'm back like Niels, check my skills. Today I'm going to integrate a really interesting integral. I was challenged by wurzelwilli to do it, and it looks like this. It has some application in aerodynamics, but the math part is much more interesting. So you see it's looking quite complicated. You have m and a as parameters, m in the exponent and a as a coefficient. So it's kind of hard to juggle around that, but we're going to make it happen. So first of all, let's just unwind this compact knot and entangle it a little bit. So I just multiplied in the top and the bottom with the square root with the square root. And now the next step is really crucial. So what I'm doing now is I just added a times x to the power of n and just subtract it as well. So this is equal to 0, so it's an operation we can do. Why we're doing this is because now we can just put brackets around this one, make it a plus sign, and now we see it's the same here, so we can just divide by this and we get 1. So that's the crucial step we're taking here. And what are we getting is the integral of x. You see we have x to the power of n and plus a times x to the power of n, so we just get 1 plus a times x to the power of n divided by 1 plus a x to the power of n. And I'm already just gonna separate it, so later we have a little bit less work. So I'll just take this in from the end. So this is the first part, this is this part. And now since this is the same, this just equals to minus 1. So we have minus 1 x square root of x times the square root dx. And so now we have two terms here. It's a little bit easier to take care of. Here we only have the x to the power of n times some coefficient, and here we just have a 1 at the top, so it's much easier to calculate with this one. So we're just going to do it by parts. I'm just going to call this, the first term is 1, and this is going to be 2. So we just got to integrate each of them and add them together, and it's going to equal to our final solution. So I'm just going to do that here. I'm going to start with the number 2 because it's a little bit easier. So we have minus 1 over x times the square root of x to the power of n minus 1 dx. And I'm just going to substitute the square root here. So I'll call this y. So y is equal to the square root of x to the power of n minus 1. And we're just going to differentiate this. So the derivative is dy. And the square root, we got to differentiate it first. We get the following expression. And now the inner derivative times n to the power of xn. And don't forget the dx at the end. Really important. You need this. Oh yeah, afterwards. Io. So we get this expression, and I'm just going to reform this to make it fitting this this part better. So we see, we have a minus 1 at the top. So because when we derive it, we need to decrease the exponent by 1. But instead of writing minus 1 here, I'm just dividing it here. So now we see a lot of similarities to this integral, except this part is kind of annoying, so I'm just going to put this one on the other side. So I'm gonna, oh, and I forgot a 2 here, because this is the square root, we need to add a 2, or need to have the factor of 2 here. But I'm just gonna put it on the other side, so we're gonna have 2 over n like this, and I'm also gonna put this on the other side, because we don't have an x to the power of n here. We're getting the following expression. Now we just gotta put this in terms of y. We can do that with this equation. I'm just gonna rewrite this. So, oh, it's m, yeah. So I have x to the power of m. So y squared plus 1 is equal to x to the power of m. And so I can just put this in this one. I'm going to write it here, just so we can still look at this. So dy over y squared plus 1. And now we can just put this and insert it in here. It's basically the same. And I'm just going to write this then instead. So we get minus the integral of 2 over m dy y squared plus 1. As you know much about integration, you would know what this integral is. If you don't know, or if you're starting to learn integration, you might not know it, but I'm going to explain it to you. It's rather simple, or very nice. So let's just say y is equal to the tangent of L. It's a really nice letter, so let's call it L. And we're going to derive this dy, and now the derivative of tangent of L. You can really easily derive it from its entity. It's equal to sine over cosine, and we just use the product rule. So first we're going to derive only the sine. The derivative of sine is cosine, so you have cosine over cosine is equal to 1. And next we're going to use the product rule and then the chain rule. So we're going to derive 1 over cosine of L, and we're going to keep the sine of L. So that doesn't change. And because it's in the bottom, we need to have a square. So it's cosine squared of L, and minus because it's also on the bottom. And now we need to have the inner derivative, and the inner derivative of cosine, or the derivative of cosine, is minus sine. So we have sine here already, so I'll just put a square here and put a plus here. Okay, and this is just the tangent squared, so the derivative is 1 plus tangent squared of L, and that makes things really easy. Oh, and I gotta put a dl here at the end. So I can just rewrite this. So for dy I'm just plugging this in, and for y I'm plugging a tangent in. I can write this in front because it has it's not depending on y or L. So 1 over 2L dy was 1 plus tangent squared of L, and the y is equal to tangent of L plus 1, and it's the same. So that's why we're using it. That's just a really nifty property of tangent, that when you derive it, you're gonna get the derivative of tangent is 1 plus tangent squared. So we're using this property, and this is equal to 1. So the whole integral here is equal to 1. This is equal to 1, and so we get the integral of dl, and that's just plain simple. This is just L. So 2 over m times L. What is L? We can get the expression for L from this equation. So if I'm just applying the arctangent, I get arctangent of y is equal to L. Okay, so I got this. So what is y? Y is the square root of x to the power of n minus 1. So the second integral is equal to 2 over m arctangent of the square root of x to the power of n minus 1. So 2 is equal to this expression, and now we're going to tackle the first integral. So we're going to use a similar substitution. So this still looks really common. We're going to find this one here, and what we did earlier is we put the x to the power of m on the left side, but now we're going to keep it on the right side because we have it here. So that makes the substitution a little bit easier. So I'm just going to put this away, and now I can erase this, and so I can substitute this expression with those terms, and I can substitute this by using the x to the power of m I just got earlier. So it's pretty similar. I get 1 plus a. So this whole is going to cancel out, and we're just going to have 2 over m, or 2 over m, and then I'm going to have 1 plus a, and now y squared plus 1 dy. We can simplify this a little bit so it looks nicer. I'm just going to put this in front as well. So I get 1 plus a times 2 over m, just write it in front, and over 1 plus 1 plus a, because of the a here, and then plus a times y to the power of 2, or squared. And we see this is really similar to the formula we just got before. It looks quite similar to the derivative of tangent again. We just got to rearrange this a little bit. So what we're going to do is I'm going to divide this section by 1 plus a, and so I get a 1 here, and then I can use the same substitution I did before. So really easy. We get the factors in front, and now I'm just going to divide it. If I divide it by 1 plus a, I need to divide it also here by 1 plus a. You can just do the calculation yourself to understand that. And so we get a over 1 plus a y squared dy, and this looks pretty similar, but we got to change it a little bit because we have a coefficient here now. So it's not going to be y equals tangent of L, it's going to be the square root of a divided by 1 plus a is equal to the tangent. So that changes a little bit. Now we get the derivative of this. It's not going to be dy, but it's going to be a over 1 plus a, the square root of that. So this is equal to tangent of plus 1 plus the tangent squared dl. And yeah, so we can just start plugging it in again. So let me think about this. We get for the dy, I'm just gonna put this on the other side. So instead of writing this here, it's easier to plug it in as just dividing it by a plus 1 plus a, the square root. So it's a little bit easier, and I'm gonna substitute this term, because it's squared, it's going to be exactly the same as here. So let me write it down. This cancels out. We get 2 over m, square root of 1 plus tangent squared of L, and the dy is going to be 1 plus tangent L squared times the this, or we can just take the reciprocal, so it's going to be 1 plus a divided by a dl. So this cancels out, this is 1 again, and this we can write in front, and so we get a similar expression to down here. Let me write it down. So this one is equal to 2 over m times 1 plus a divided by a, and now this is equal to 1, so this is L. L, like we've seen before, is just going to be arctangent. Oh, because we changed it here in front, we also got to change it here. This is going to be equal to L this time. And yeah, we can just write that, and then the y is going to be the same as before, square root of x to the power of m minus 1. So we get 2 over m, 1 plus a divided by a, and arctangent of equal to the square root of x to the power of m minus 1 times, and now the factor we got here before, so a divided by a plus 1, like this. Okay, this is actually our integral, so I can rewrite this. We calculated 1 just now and 2 before, so let's just have a look. So 1, the integral of 1 was 2 over m, 1 plus a divided by a, square root of arctangent of a divided by 1 plus a, times the square root of x to the power of m minus 1, right? And the second one was not a plus, but rather a minus. So we shouldn't forget this minus, and the minus is here, so the second one is minus 2 over m arctangent of x to the power of m minus 1. Yeah, so that settles it. It's a really complicated looking result maybe, but you see, as soon as we start separating the integral in smaller parts, we could solve the problem. Divide and conquer is the way to success here, and yeah, it was a pretty nice integral to calculate. I just found some wonky videos online telling you how to do it. They were really long, so I didn't want to watch them. I hope this is a little bit shorter and a little bit more handy to understand. And yeah, I'm looking forward to maybe doing more math videos. Bye.